Yeah, highlight some problems. This is you guys showed me 4 through 8, but I wanted to just make sure you guys are good with the derivative of inverse at a point. This is page 6 in your packet. You guys already did this for homework, but and for first semester, I want to make sure that you can have any questions here. So number 9. So here's the big picture with derivative of inverse at a point. Is the fact that if you have an inverse function, this could be what an inverse function could look like in the sense that these two curves are, you can kind of imagine them, if you can imagine folding over the line y equals x, the two graphs are overlap each other. So visually, this is what function and inverse look like. So there are some visual connections between their location and their slope. So the visual connection is that their order pair, if it's a function and it's inverse, they're always going to have these special properties. And the fact that any order pair that you can imagine on the function, the flipped version of those order pairs will exist on the inverse. So if there's an order pair 1, 4 that lives on the function, there must be an order pair 4, 1 that lives on the inverse. There's an order pair -2, 5. There's going to be a 5, -2. So, so that's, I call them corresponding points. So that's demonstrated with these order pairs here. If I have an order pair AB that lives on a function, then on the inverse, there must be an order pair B comma A. Now, at these corresponding points, there's also a special relationship in terms of their steepness or their slope. So let's say this, now you can tell that these are both positive slopes, right? So they're both going to be the same signs. And if this is a slope 7, then guess what this slope will have to be? 1/7. Yeah, it's always going to be that numerical relationship in terms of be the reciprocal with each other. Okay? And this is only going to happen at these corresponding points where their order pairs are flip-flop versions of each other. So the way I go about solving these problems is you're always going to be given what you're looking for. So this is always what you're looking for. And then from there, I'm just going to fill out the rest of the chart. And by the time I make my way down here, I would have already gathered enough information where I can find what that slope I'm looking for. So usually with these problems, you're asked about the inverse derivative, but what's given to you is on the function side. So you have to gather information on the function side and then use that numeric slope to figure out what your answer or what your target slope is. Okay, so number 9, given our function is 2x cubed minus 3x, if h of x is the inverse of function f, so they've established that h and f are inverses of each other, then h prime of -1 is equal to. So that's what I'm looking for. I know I'm starting on the inverse side of things. So I'm going to start here at the bottom right corner here. H prime of -1 is my unknown. Now, -1 is the x value of my inverse. So I'm going to establish that x value of the inverse. But that means that what? -1 is also the what of the original function. The y value, right? So I know that f of some x value is equal to -1. So without looking at anything else, if I know that this is what I start with, then I know that I can fill it up to this point. I know that -1 is the y value of my function. So now, how can I use this to help me move forward? That's my next step. How can I find this x value here that I'm looking for? Put -1 in for what? And for the y, yeah. So -1 will go in for the y. Kind of working backwards here. We have the y value information, and we're working backwards to find the x. And the reason why we want to solve for x is because if we solve for x, then we can find f prime of x. We can find the slope using this derivative, find the slope at a point, and then from there, we can use that slope number to get to our answer. So we know that -1 is equal to 2x cubed minus 3x. A little bit of guess and check here. I'm going to just set this equal to 0. Do some x values here. If 0 doesn't work, then try 1. If 1 doesn't work, then try -1. It'll always be an easy integer value that's close to 0. So if I plug 0 in, 0 doesn't work. If I plug 1 in, 2 minus 3 is -1, -1 plus 1 is 0. That works. So it's like 1 works. So my order pair is 1, -1, which means that on the inverse side, it must be -1, 1. So if I can find f prime of 1, then this slope will lead me to this slope. So f prime 1 now gets a little bit easier. I can find f prime of x first, then I can plug 1 into the derivative. Okay, so the slope at 1 is 3. So therefore, the derivative of h prime of -1 must be what? Reciprocal, right? 1/3. Okay, number 10, same process. It's just a little bit easier because all the information is already given to you. We just have to kind of fill out our chart here. So I'm trying to find the derivative of f inverse at 2. I know that 2 is the x value of my inverse function, which must mean that 2 is the y value of my function. So let's see what information is given that allows to fill some of these blanks here. We know that f of 1 is equal to 2, so that's helpful. Therefore, if I can find f prime of 1, then this slope will lead me to this slope. Okay, so notice that f prime of 2, that's trying to throw you off, right? F prime of 2, that's not going to make sense for us because 2 is the x value of my inverse, but it's not the x value of my function. So this is kind of a distractor. Okay, f prime of 1 equals 3. That's what's going to help us. So if the slope at 1 is 3, then the slope of the inverse at 2 must be what? It's just a coincidence that these are the same numbers. Your answer is not always going to be 1/3. Just kind of coincidence. Okay, so you guys finished pages 5 through 8. Are there any questions from these pages? Any ones that you want me to go over with you? So today our focus is going to be related rates. So let's go to page 9. So related rates, it's been a while, right? So limits, related rates, derivative inverse at a point, all this we covered all the way back in September, October. Okay, related rates are problems where we relate the rate of change of a dependent variable with the rate of change of an independent variable time t. So here are the steps. We identify the equation that relates the variables. So we always start off with some equation that we recognize, whether it's Pythagorean theorem or volume of a cube or surface area of a sphere or a trig equation. And it's always going to have these kind of word problem feel to it because it's always going to be in relation to time. Okay. So as time moves forwards, this rate is decreasing, this value is increasing, and then it's asking for some, usually dealing with some rate of change with respect to time. So we're going to take that equation that we start off with either a geometric or algebraic equation. And then we're going to find the derivative of each variable with respect to time t. Solve for the variable in the new derivative equation. So number one, this is the problem that we started related rates with all the way back. This is our first example of related rates. Let's see if we can remember our steps here. So we have a 15-foot ladder that is sliding down a building at a constant rate of 2 feet per minute. How fast is the base of the ladder moving away from the building when the base of the ladder is 9 feet from the building? So here's the direction of motion of the ladder. The ladder is moving down the wall, and the base is moving away from the wall. So sliding down the wall. So we know that Pythagorean theorem is going to be the equation that's going to relate each of those variables that we're dealing with. Okay, so we start off with a squared plus b squared equals c squared. Every variable is going to get touched by or impacted by time. So let's go ahead and find the derivative. And as soon as we find the derivative, we're going to attach a d over dt for that variable. Okay, so x squared becomes what? Derivative. 2x times x dt. Y squared becomes 2y dy. Then 2z. So x, y, and z represents the length of the base, the height, or the hypotenuse of the triangle at that moment in time. Dx dt, dy dt, dz dt, that represents how fast that length is changing in terms of its length. Okay.
Basically, the rate of change.
Yeah, it's the rate of change of the length of as time passes. Right. So it could be 2 feet per minute or negative 2 feet per minute. So let's go ahead and label all the variables that we're working with. Sorry, x equals space, not y. Okay, so x equals, y equals, z equals. Okay, so if we can list out the values of, our goal is to basically fill out 5 out of the 6. Because if we can get 5 out of the 6, then we can use this equation to find the last one that we're looking for. Okay, so let's read the problem again. 15-foot ladder, what is that going to be associated with? Sliding down at a constant rate of 2 feet per minute. What do you think this is going to refer to? It's sliding down, though, sliding down dy dt. And what's happening with this vertical distance on this triangle? Decreasing, right? It's not because it's the moving down. I want us to make sure that we don't associate direction with the sign. You want to associate with what's happening to that value. Okay? If that value is getting smaller, you want that rate to be negative. If that value is getting larger, you want that rate to be positive. So therefore, we can say dy dt is what? Negative 2. How fast is the base of the ladder moving? What are we looking for? What's our ultimate goal here? Yeah.
X dt. We know it's not just x because you see the word fast, you see the word moving. You know there's some sort of a rate going on. Yeah. Okay, so dx dt is what we're looking for. X equals 9, right? X equals 9, yeah. When there's a moment in time when the base of the ladder is 9 feet, so 9. I just want to ask real quick here, dx dt, what do you expect out of dx/dt? Do you expect dx/dt to be ultimately at the end? I mean, we're gonna have to solve it using the equation, but what do you expect out of this? Do you expect this to be a positive rate or a negative rate? It's growing, right? Some students we associate left with negative, so we just think, oh, left, that means it's negative. dx/dt direction doesn't matter. It matters what's happening to that length. Okay, so if we can find y and dc/dt, then we can use this equation that we built to find dx/dt. How do you think we can find y? Pythagorean theorem, right? A squared plus b squared equals c squared. So 9 squared plus y squared equals 15 squared. We use our calculator. It's going to end up giving us 12. And what do you think dc/dt is? Okay, 0. Why is it 0?
Is the ladder growing?
Is the ladder changing? Yeah, it's going to be 15 feet at the beginning of the problem. It'll be 15 feet at the end of the problem. So it doesn't change, right? So the rate of change is 0. That hypotenuse length is not going to change over time. All right, so now it's just a basic equation that we're solving. Replace every unknown variable or every variable with what we have provided, what we've gathered, and then we can solve for dx/dt. Okay, you guys want to try that? Yeah. Okay. So above is positive, below is negative.
This one is both, it's like below and above. So I would recommend.
Your shaded region may not be correct.
Okay.
You're only looking at what's between the graph and the x-axis.
Okay. I felt anything. This one says -5, but it doesn't go to -5.
Yeah. So sorry.
Six.
We should get positive 8/3 for dx/dt. Any questions with one? Okay, let's take a look at the number 2. Number 2, we have a beach ball that's deflating at a constant rate of 10 cubic centimeters per second. When the volume of the ball is 256/3 pi cubic centimeters, what is the rate of change of the surface area? So we have the surface area and the volume formula for a sphere given to us. So we know that eventually we're going to have to deal with all these derivatives. So let's go ahead and get the derivatives out of the way. And that way we can get all the calculus completed and just fill in and find the missing pieces that we need. Okay, so let's go ahead and find the derivatives. We know that V and R will both be impacted by time. So let's go ahead and find the derivative. V becomes what? dv. 4/3 pi, this is no need for product rule, right? 4/3 pi is just some number that's sitting in front of R. So 4/3 pi is going to stay. The power rule is going to get involved with that R cubed. So what does R cubed turn into? 3R squared. Anything else? Yeah, every variable gets impacted by time, so R becomes, or R needs to involve dRdt. Do some cleanup here. dv dt equals 3's cancel out. I get 4 pi R squared dRdt. Okay, let's go ahead and build the surface area equation, or get that out of the way. S equals 4 pi R squared. Let's find the derivative. S becomes, what's S's derivative? It's the 2. 4 pi stays, we bring the 2 down, so 8 pi R. Okay, so the calculus is done. Everything's in front of us. We just have to figure out what variable we're solving for, and what information we can use to solve for that variable. So let's go back and read the problem here. A beach ball is deflating at a constant rate of 10 cubic centimeters per second. What do you think we can assign that to? And here's the hint. The hint is cubic centimeters per second. We want a unit that has dVdt, yeah. So cubic centimeters, that's referring to volume. Time, seconds, so dV over dt. So what can we say? dVdt equals what?
10 centimeters.
Close.
10 centimeters.
And the ball is deflating.
So minus.
Yeah, negative, right? So decreasing. Yeah, the rate is decreasing. Right. When the volume of the ball is 256 over 3 pi, that's just what? It's just V, right? So 256 pi over 3. What is the rate of change of the surface area? What are we looking for? The SDT. Okay, so that's the unknown. So here's our ultimate goal. Our ultimate goal is to solve for the SDT. Now, ideally, if we can just plug in R and dRdt, we can be done, right? But looks like R and dRdt are not provided for us explicitly, but they gave us dV/dt and volume. So do you think there's any way that we can use these two pieces of information along with the formulas to eventually get to what we need with R and dRdt so that we can plug that in and solve for dSdt? Let's start with V here. How does this volume value help us out in terms of finding eventually one of these variables that we're hoping to find? Okay, we know the volume at this moment in time, 256 pi over 3. We have a volume formula here. Right? So if I replace V with 256 over pi, or 256 pi over 3, I can solve for R. If I solve for R, then that's one piece of the puzzle for my problem. Okay, so if I cross multiply, clean this up, the pi's cancel out, the 3's cancel out, I get 256 equals 4R cubed. Divide both sides by 4. Yeah, 64. Okay, the cube root. So r is equal to 3. Sorry, r equals 4. 4 cubed is 64. So if I have r, that's one thing that I need. Eventually, that can help me get to ds dt. The next part is how can I get to dr dt? Because I don't have that given to us. But it do give us dv dt. Is there any way that we can take this and get to where we want to go? We have our dv dt formula, right? I can replace dv dt with -10, replace r with what? What's our radius? 4, and then we can solve for dr dt. If we solve for dr dt, then that's the last piece that we need to find. Okay, so dv dt gets replaced with -10. R gets replaced with 4. And if we clean this up here, we get -10 equals 64 pi. Reduce that, -5/32 pi. Notice that pi is still in the denominator. We can't just move that up to the top. That's not the same thing anymore. It needs to stay in the denominator. dr dt is -5/32 pi. And then that's the last piece that we need because ds dt requires yeah, ds dt requires r and dr dt. So I have my radius 4, I have my dr dt, which is -5/32 pi, and now we can solve for ds dt. Things up all the way to -5. Now, the units of measure here, surface area, focus on that word area. Area is a two-dimensional unit, so centimeters squared, time is seconds, so centimeters squared per second. The beach ball is deflating, so the volume is decreasing, and it makes sense that the ball is getting smaller, so the surface area is decreasing. Interpret how the way you want to. All right, let's look at number 3. This is one that requires similar triangles with cones. So these are cone problems are the ones that most and kind of labor intensive. It has most amount of work involved. Okay, so water is poured into a cone container at a rate of 10 cubic centimeters per second. The cone points directly down and it has a height of 30 centimeters and a base radius of 10 centimeters. How fast is the water level rising when the water is 4 centimeters deep? So okay, the thing with cones is that we have a lot of variables in play. So V is changing, R is changing, height is changing. So the goal is we want to get it down to just 2 variables. And we want to reduce the number of variables in this problem by using similar triangles. Similar triangles will allow us to narrow down our equation so that's easier to work with. Because if we can build a relationship between the radius and height of the water level inside this cone, then we can replace one of the variables and then it becomes a lot easier to work with. So I want us to understand that there are 2 cones inside this problem. You have the cone of the container, which is not changing, right? The dimensions are what it is. The water inside the tank also forms the shape of a cone, and that's what's changing, right? So as water is being poured in, you can expect the height of that the height of the cone formed by the water is increasing, and also the rate or the radius formed by the water level inside the cone is also changing. So if we just focus on just this right triangle portion of our problem, we can kind of build out the relationship that we have for our similar triangle. So it's going to focus on just that portion there. So what is the radius of my tank? 10 centimeters. This is not changing, right? So we can put a 10 there. The height is what? Okay. The reason that we can just go ahead and put those numbers there is at the beginning of the problem, it's going to be 10 and 30. At the end of the problem, it's going to be 10 and 30. But the water level is not, it's changing, right? As more water is coming in, the height at the beginning of the problem is not going to be the same as the height at the end. So we want to let variables represent those because those are changing. Okay, so we can say this, we can say the radius of the water level is to the radius of the tank as the height of the water level is to the height of the tank. So now we've built a relationship between the two equations, the two variables, and this allows us to solve for one in terms of the other. So if I cross multiply, I get 30R is equal to 10H. Now we're going to pause here because we don't know whether to solve for R or solve for H. And we need to gather some more information before, now either one can work, it's just one way is going to be a little more efficient than the other. So we want to kind of use context clues to decide, okay, which is the variable that we have information about and which one will make things go a little faster. Okay, let's go back to the problem here. Let's gather some information. Okay, water is poured into a tank at a rate of 10 cubic centimeters per second. What variable is that referring to? dV/dt. Positive or negative? Positive, right? The volume inside the tank is growing, so dV/dt is positive. How fast is the water level rising? What are we looking for? Then it would say how fast is the radius of the water level rising? Yeah, or yeah, dHdt is the water level rising. So rising is a vertical motion there. So dHdt is the unknown. When the water is 4 centimeters deep, that's just what? SH. Yeah. We gotta be careful here because this 4 centimeters is not going to be used at all until the end. Okay, so do not use until the end. The temptation is you want to start putting the 4 wherever you see the H. And if you insert the 4 in for the H, then what you're saying to the problem is that the height of the water level is always going to remain 4 from the beginning to the end. And we don't want to, we know that's not true, right? If water is pouring into the tank, it may be 4 centimeters at one moment, but before it and after it, it's going to be a different value. So we don't want to use that 4 until we found the derivative when our problem is locked into a specific moment in time, and then we can use that 4. But this is helpful though, because we do see information on the H side of things. And we don't have a lot of information on the radius side of things. So if we go back to our volume equation, which variable do we prefer to keep and which variable do we prefer to remove? Yeah, prefer to keep the H because all the data is on the H side of things. Now, if we did the opposite, we can still get to the answer. It's just a few more additional steps. So it's a little bit faster to recognize, oh, okay, I already have all this data on the H side of things. So if I can get rid of R, then things will go a little smoother.
Why is pi like pi over 3 r squared is the pi over 3 r cubed?
Right. So the volume formula for a cone is it's pi r squared, and then the height is from h over 3. So that's just the formula for. But we still have yeah, circle is pi r squared, and then h is that height. So you still get the area, and you still get that third dimension there. But pi r cubed would be more for like a sphere. Okay, so we want to get rid of the radius, right? So what if we just solve for radius, then I can find a replacement for radius. So if I solve for r, back to this established relationship that we have, r equals 10h over 30. So r is equal to what? H, yeah, 1/3 h or h over 3. So we're going to take this and replace the r. Let's rewrite our equation. V is equal to pi over 3. R gets replaced with, don't forget the what? Anything else we need to include? Anything else?
The square.
The square, yeah. So sometimes we forget about the squared here. So okay, we do want to find the derivative, but we should do some cleanup, right? I mean, if we found the derivative here, you got to go through product, chain, and it's just a whole mess, right? So there's no need to do all that messy process. We can just clean it up and just rely on power rule. So let's just clean this up. V is equal to we can merge the variables together, combine the coefficients together. So the 3, the 9, and pi, I'm just going to make it all come together as pi over 27. And the h squared times h can be combined to be what? H cubed. So a much easier equation to find the derivative. Okay, so now related rates. Every variable is going to get impacted by time. So v becomes the dv dt. Pi over 27 is just some number. It's just going to hang out in front. H cubed becomes what? Squared. Don't forget. What else do we need?
You plug in the h.
Well, are we done with the derivative yet? Is there anything missing?
Yeah.
Yeah, the HDT. Okay, so now the calculus is done, right? Because everything we need is in front of us. We have dv/dt. We have h, and then we have the variable that we're looking for, dh/dt. So replace dv/dt and h with the numeric values, and then just algebraically solve for dh/dt. Leave pi out of your calculator. but it will stay in the denominator. So you can just do 10 times 27 divided by 48. I get 45/8. Careful that you don't just let that pi float up to the top. It's going to stay in the denominator. Height is a one-dimensional unit, not like area or volume, so it's just going to be centimeters per second. Okay, let's do one more here. This is number 4 is going to be a trig related rates. The thing with trig related rates is we start off with a trig equation, we find the derivative, but then there's a special process that we go through when handling trig related rates. But let's start off here. In the right triangle shown, the angle theta is increasing at a constant rate of 2 radians per hour. At what rate is the side length x increasing when x equals 4 feet? So we know we're looking for dx dt. We have theta involved. We know that anytime we see theta and related rates, we got to build a trig equation. So we're always going to start off either sine, cosine, or tangent. Right. So look at theta, look at x, look at 5, look at where they're located in relation to theta. What's going to be our best fit? Sine, cosine, or tangent? Sine, right? Because sine of theta is equal to opposite over hypotenuse. We have all that data in front of us. There's no adjacent, so we don't want to use tangent or cosine. Okay, so that's our equation that we're going to build our derivative from. If it helps, you can write that as 1/5 x. Okay, let's find our derivative here. Sine theta, what's sine's derivative? Times. Yeah, every variable gets impacted by time. 1/5 x becomes. Okay. All right, let's gather some information here. Angle theta is increasing at a constant rate of 2 radians per hour. Okay, what can we assign this? What variable is that referring to? D theta dt. You see time component involved with theta. At what rate is the side length x increasing? What are we looking for? Looking for dx dt. When x is 4 feet. Now, we know what we're looking for. We are looking for dx dt, so that's showing up in our equation. We have d theta dt. But what's another missing piece that we need to resolve? Yeah, not just theta, but cosine of theta. We want to find a replacement for this entire cosine of theta. So to find that replacement, we're going to find a ratio for the triangle. So we're going to go back to our triangle. I'm going to redraw a different a triangle with different things filled in. Okay. Now, this is a moment in time here. So x is 4 feet. This is not going to change. Okay. What's the adjacent side going to be? All right, Pythagorean theorem, right? A squared plus b squared equals c squared. So now the question is, can I figure out what cosine of theta is based off of this triangle? Cosine theta equals what? All right, adjacent over hypotenuse, right? Theorem of fun. Okay, we make our substitutions. Cosine theta gets replaced with 3/5. D theta dt is 2. And then 1/5 times dx dt. Clean this up. 6/5 times equals 1/5. 6/5 times 5 is going to be 6, so dx dt is 5. sorry, 6. Units of measure. Second. Or feet per hour. Okay, so your homework is to finish pages 9 through 12. Okay. I can get your phones. Your homework.
Oh, yeah. Yeah, that's all it's, yeah, how it's in this other. Are you going?
Connor, you got pages 5 through 8.
I paid attention before to ones that, one is one.
It will be come back later.
5 through 8.
I'm gonna start trying this. Please try it. I can come to your advisement and show you.
Okay, thank you.
Yeah. You might just be told.
It comes back to service. I got this until we rest your compliments and looking at our section. I'll be fine for that. Fine.
That's like no, that I think so. I'll do
Thanks, guys.
You're about to do pick off when you
What happened?
You're about to do pick off when you basically like the players can't move until the receiver has the ball. Now, I guess.
Yeah, look at that.
That's crazy.
I'm doing that to protect the.
I think increase the turns and.
Thanks.
But yeah, XFL did it.
Oh, interesting.
Yeah.
I wonder how that's gonna